Okay, to start with some announcements, remember that your final exam is on Friday of next week. We've got, I think, the second to last exam slot of finals, so from 10:15 to 12:15. And the exam's comprehensive. You can bring 3 pages of notes, and it's going to have both concepts and problem solving from the entirety of the course. Any questions on that announcement? You've just submitted your last homework assignment, and I'll post the solution to that today so that you can check to see if you got the right idea, and I'll try to grade that as quickly as I can, but I'm sure you know as well as I do that things get pretty crowded at the end of the semester. So today we're going to be using BioWin to do some simulation modeling, and as I already mentioned to you, I'm not a power user of this software. I've had it in my hands less than 24 hours, and I've put together a demo that I think is going to be useful and interesting, but there's a lot of things that I haven't yet discovered in the software, and there very well could be some error messages or problems that pop up along the way that just stop us in our tracks entirely. But with all that said, I'm hopeful it can be kind of interesting because the wastewater treatment is such a complex process with so many different chemical and biological reactions happening, so many different types of reactors that you can have in a treatment that having a model like this that allows you to really quickly optimize and iterate is extremely valuable. All right, so here is the setup that we are going to try and simulate. We are going to start from scratch. You've just opened a pre-built model to verify that the program worked, and we may come back to that later, but we're going to start from just a white page, blank screen, and put together secondary treatment in a wastewater treatment plant. And you can see that I've got the values defined here of the flow rate, the BOD, and so on. So the chemical and biological characteristics. And we're going to interrogate the system that's defined here in green to see what does it do for the wastewater that's coming in. How much does it bring down the BOD? How much does it bring down the nutrients? How does it affect the total suspended solids, the volatile suspended solids? We'll just evaluate the given design, and then we'll try to optimize. We'll try to reduce the size of the aeration basin, for example, to see how does the performance start to suffer if we make the aeration basin smaller. We'll start to reduce the recirculation of sludge to see how does that affect performance and see what we can get away with and still meet a required standard. All right, so to begin, we're going to start with just a blank network. So here, go to File, New, and that'll toss out what we had opened, and now we've got a blank screen. So in the Configure tab that's on the top here, we're going to begin drawing using these elements that are across the top. And we're going to start with an inflow that is influent BOD. So it looks like a pipe that's kind of yellowish and red. This symbol, once you click on it, then bring the cursor down into the main project window, not too close to the top, bring it down a little bit, and then just drop it. So it should say influent, then BOD. The 0 just means that it's the first element that we've created. I don't know why they start at 0, but as we drop additional things, there's a default name and then a numbering. So let's drop that influent BOD, and then back up here to the top. If you hover over something, it'll briefly tell you what it is. We want to next put a bioreactor. So this green one, which shows like the little air bubbles in the icon. So if you go to bioreactor, we're going to next drop a bioreactor. Then we're going to put in a clarifier. So scroll across, and we're going to look for the ideal clarifier, which is this one. Ideal clarifier. Okay, then we're going to do an effluent, which is this blue water coming out, the clean water. So we drop an effluent. We're also going to drop a sludge that's going to be coming out. And then a splitter, a flow splitter. Put that down below between the bioreactor and the clarifier down here. And then we need to connect everything with pipes. So here is the pipes. I don't know why it looks like a little airplane icon, but here's the pipes. And when you get close to something that can be clicked on, the cursor icon is going to change. It'll have a little target on it. See how it's got a little target as I get over there? So click on from the influent to the bioreactor, and then click from the bioreactor to the clarifier, from the clarifier to the effluent, from the bottom of the clarifier we're going to go to the splitter. Now, I'm not sure I like that pipe. I want it to go to one of the other inputs. So I'm going to use this selection tool here. I'm going to select that pipe and delete it. Okay, so I'm going to try again with the pipe. So the pipe from the bottom of the clarifier, let's see if I do it maybe to this one. No, I don't want it there. Maybe one more time. I guess it could just be if I drag the splitter to the side, it'll be less confusing. Yeah, I guess it's maybe a matter of location. Okay, so I guess I've just given away something that you can reposition these. You can move them around and it kind of changes the schematic. You can move the location of the pipe if you need to based on these. We're going to put labels on things in a bit.
Can you rotate the splitter?
I'm not so sure that we can, but that's all right. It's just really a schematic. It doesn't have to be, you know, like to scale or with hydraulic grade lines in mind or anything like that. All right, so let's now connect the dots from the splitter to the sludge with a pipe. So from the splitter to the sludge, and now we need to recirculate back into the bioreactor. So last pipe from the bottom up to the bioreactor. All right, so this is activated sludge. This is secondary treatment. Secondary treatment is, that's strange that the pipe from the clarifier, I'm hopeful that that knows it's coming from the bottom of the clarifier. We'll just have to wait and see. Okay, so now we have to start putting in the characteristics of the flow. So if you double click on an element, it brings up like kind of an editing dialog box here. We're going to put in constant flow data. You can define variable flow data, like that the flow rate goes up and down through the course of the day, and you can even tell it how the BOD or the nutrients change over the course of the day in an unsteady state simulation. But we're going to just do a steady state simulation where maybe there's some sort of flow equalization upstream, or this is a waste just for whatever reason that the flow characteristics are constant through the day, is what we're assuming for simplicity. So leave it on constant and then edit data. And this is now where we can start to put in the details that we know about the network. For instance, that the flow, you can see down here at the bottom, the units are cubic meters per day. And so our network is 35,000 cubic meters per day. And for the BOD, we want to put in a total carbonaceous BOD of 259. I might have, did I say 127 on the handout? BOD 127. So let's change that to 127. All right. Total suspended solids. The total suspended solids is 150 and volatile suspended solids is 100. So 150 for total suspended solids. Oh, good. 100 for volatile, 150 for suspended. And then we're just going to leave the nutrients with the default. Nitrogen is 40 milligrams per liter. Phosphorus is 6.5 milligrams per liter. All right, so we're also going to put some tags on it, and these tags will allow us to see underneath the icon the characteristics that we've just defined. So click on the tag location should be below, and then you turn on certain tags that we want to be able to see. And what we're going to tag is the total carbonaceous BOD. We're going to turn on the tag for the nutrients, and so the total kildol nitrogen, which, by the way, the total kildol nitrogen, it measures the nitrogen that's in the form of organic nitrogen and inorganic nitrogen in the form of ammonia or ammonium, but it doesn't include nitrate or nitrite. So total kildol nitrogen, the total phosphorus, and let's also put on total suspended solids and total and volatile suspended solids. So then just below that, it's now identified the BOD that we wanted, the 127, the nutrients, and so on. Okay, so we've defined the influent characteristics. Next, let's tag all of the pipes. So we're going to have to one by one double click on each pipe and then put a tag below the pipe and turn on the tag of the state variable flow. This will be helpful to us just to see when we are splitting up the flow down here to make sure that the correct amount is going as sludge, the correct amount is being recirculated, and so on. Okay, so let's click on all of the pipes, and this is effectively annotation that we're adding with the flow. Now, it doesn't know yet all of the flows, and so it's going to have just kind of a default value, 100 or 1 or whatever. But we'll have it do the calculations, and it'll figure it out, what's the actual flow, once we get to that part. Okay, now this is the one, oh, okay, yeah, all right, tag. Oh, that's the splitter that I pulled up, not the pipe. Yeah, I'm concerned that the pipe's not correctly connected, so I'm going to draw a pipe. I think I've got to delete my splitter and put in a new one. It'll delete all my pipes, but that's okay. So I'm putting in this splitter again so that I can draw the pipes over again. So I've got one going from here to, okay, that's definitely flowing out now correctly. One from here to the sludge, and then one from the bottom back up to the bioreactor. All right. So hopefully you didn't have to do that, but remember what we were doing is we were annotating all of the flows with just the label of how much is going through there. And you have to tell it the location as below. I don't know why the default doesn't bring it up, but you do have to tell it below, and then it'll show. I guess you could go with above if you want, but the point is you have to give it the fixed location that you want to see. below flow rate. All right, so we've got all of the flows annotated, and if we move the location of this, it will kind of adjust the diagram a little.
If you move it down, I would flip it.
Yeah. You can go down like that. There we go. That's more obvious. We can see the arrow now. Okay, so we've defined just the influent, but we haven't yet told it how big the bioreactor is. It doesn't know, for example, what dissolved oxygen concentration to assume in the bioreactor. We haven't yet told it the size of the clarifier, so we need to do all of that. So let's just double click on the bioreactor, and it brings up where you can begin to type in the characteristics of it. So we're going to go with a volume and depth being defined. And our volume of this reactor is 4,000 cubic meters. And then the depth, 4.5, we're leaving it at that, but the width is 15 meters. If we go back here to the characteristics of the aerator, the volume, the depth, and the width is what we're going to tell it. Under operation is where you can tell it what to assume about the amount of dissolved oxygen inside the bioreactor. So there's a lot of different ways you can do it. You could tell it how much air is coming in, and then it will calculate the amount of dissolved oxygen for you based on the type of diffuser that you've defined or the airflow rate, like in terms of cubic feet per minute or something. Or you can just say, let's assume that it's a certain concentration of dissolved oxygen inside the aerator. So let's do that, just going with the default assumption of assuming that the aerator remains at 2 milligrams per liter, and we're doing calculations elsewhere to ensure that we know how much air is required to do that. One of the interesting things you can see is that you can tell it how much power is being consumed, or it can calculate the amount of power consumption. And then there's an economic model running in the background where if you tell it the price of electricity, then it can generate a report that tells you what is the cost of operating the wastewater treatment plant. And you can define things like the cost of chemicals, the cost of sludge processing. And so then that would allow you to go in and try and minimize the cost of operation by trying different combinations of chemicals to improve the performance while balancing out the economic consequences as well. So let's just leave everything default, except for, of course, we did indicate the volume that we want and the dimension parameters, but let's tag it. Let's tag it with the above. I think it would be best if we do it above in this case. Above, and then the local parameters that we want to have is the let's see, where was it? Is it a combined parameter? There's somewhere we can get at the airflow, which I thought was interesting. We may find it. In the meantime, let's have it show us the CBOD, so the total carbonaceous BOD. Go down through and get the total Kildall nitrogen, the total phosphorus, total suspended solids, and volatile suspended solids. And then, over under element specific, airflow rate. I just think that's interesting to see the calculations that it goes through to determine the total airflow rate. So the chemical parameters are under combined, element specific is the airflow rate, and when we click OK, then it will pop all of these at the top. I need to maybe bring my model down a little bit because some of these parameters are off the screen a little. So if I drag that down, then the label will come down as well. Unfortunately, I haven't found a way to zoom out any further. If you start your model too high on the screen, then you just have to drag it down until it's in the right spot. Okay, so we've defined the characteristics of our bioreactor, and you can see since it hasn't calculated anything yet, it doesn't know what the BOD in the bioreactor is. and that's okay. But we have to now double click on the clarifier, and to define the clarifier, let's give it the volume and depth. So specify by volume and depth, because what we know about this clarifier is it's got a volume of 20,000 cubic meters and a depth of 4 meters. Okay, so the volume is 20,000 and the depth is 4. That might have been the default anyway. Okay, under operation, we're not going to change anything there. This is an ideal clarifier, and we're just going to assume that we don't, it's not going to do any short-circuiting calculations inside of here. There is a different type of clarifier where I presume that it can do some calculations having to do with the efficiency of the weir overflowing and the risk of short-circuiting and so on. But in the flow split, we're going to define that there is a certain amount of the underflow, a certain amount of liquid that's being taken off the bottom of the clarifier, and then some of it will be recirculated, some of it will be wasted as sludge. So the underflow that we want to have here is 15,000 cubic meters per day. So underflow 15,000 cubic meters per day. And then let's turn on tags. Above it, we'll turn on the tags of element specific. Element hydraulic retention time. Be interesting to know. The surface overflow rate. The solids loading rate. These are all parameters about how heavily we're loading the clarifier. And we'll just leave it at that for those. So we've got the hydraulic retention time, solids overflow rate, solids retention the solids loading rate, and surface overflow rate. So the water that comes in, it's going to send a certain amount of it down, the rest of it out through the effluent. Let's double click on the effluent because we want to see the tags of the concentration. So specify that below this we want to see the tags of the total carbonaceous BOD, the total killdall nitrogen, the total phosphorus, total suspended solids, and volatile suspended solids. And so that's how we're going to know, like comparing what came in and what came out, the performance of this reactor. And we'll add the same tags to the sludge, just so that we get a view of how those pollutants are being concentrated by the clarifier. So we'll do BOD, total killdall nitrogen, total phosphorus, total suspended solids, and volatile suspended solids. All right. Oh, and I probably didn't specify the location below. There they are. I may need to zoom out a little bit now. All right. Okay, the last thing we're going to specify is down here in the splitter. We're going to tell it how much of this flow gets wasted versus how much of it is recirculated. So for the splitter, let's specify a side flow of 500 cubic meters per day. Now, which it defines the side and which it defines as the main flow, we may have to go back and adjust it, because what we want is we want to be wasting 500 cubic meters per day. So I think, let's see, I think that the bottom one is side. So actually, I don't want 500 cubic meters per day to go there. I want 14,500 to go recirculated, and then that'll make, I think, 500 of it, the balance, be waste. So here in the splitter, the flow spit's 14,500 for side if you've got like the recirculated part going out of the bottom of it. I think that this is the side and this is the main. See how it's got options for both rate inside, rate in main? So if we've got 15,000 coming in, then there's going to be 500 going out and 14,500. So we've set everything up. The first thing that we need to do is here simulate, on the Simulate tab, flow balance. And it brings up this little flow analysis window here. The play icon will have it do the calculations for flow balance. And now we can see like the flows actually make sense now. So we have 35,000 going into the bioreactor. Of that, like the out of the system, 500 is leaving as sludge, 34,500 is effluent. So in equals out, which is good. But then there's this recirculation loop where you can see that 15,000 is coming off the bottom of the clarifier. Of that, a certain fraction is wasted. The rest of it is recirculated. And it hasn't actually calculated the BOD yet. So it's reporting values, but it hasn't done the biological calculations yet. So far, it's only done the flow rate calculation. So don't be thrown off by the fact that it's saying the BOD went from 127 to 1200. We're not actually growing BOD in here. We're consuming BOD. It hasn't done the biological simulation yet. So let me pause for a second. Are there any questions so far? The big hurrah is when we have it run the biological simulation. So here on Simulate, steady state balance. Let's have it do a steady state calculation. And by the way, you can see that sometimes it needs to go through several iterations to find the solution. You can either start from just typical values or current values if you've already run the simulation once. Since this is our first time through, we'll start from the seed values and just click on the play button, solution found, which is good. And we can see that the BOD went from 127 down to 6 milligrams per liter. The nitrogen went from 40 down to about 7 milligrams per liter. The phosphorus went from 6.5 down to about 4. But there's one thing it hasn't calculated for us. Down at the bottom, there's this row of details across the bottom here. It's not yet calculating the solids retention time. So that's one last thing that we need to set up, because solids retention time is one of the key ways that you know really what's happening in the reactor, what type of bacteria are likely to set up. And so under the Calculators tab, you see where it says Main, Configure, and Calculators. Click on the Calculators tab, and we're going to do a new solids retention time. So new SRT. And what we have to tell it is where are the solids in the system. It doesn't necessarily know what to assume for where the microorganisms, like the mass of that is, especially for really complicated systems where you have like parallel streams or maybe things that are operating in sequence. You'd have to be pretty careful in setting it up. Ours is going to be simple. So the first thing that you select elements for total mass. And what we're going to, for the total mass, we're going to indicate that the mass of this biological system exists in the bioreactor. So you expand that and click it with this arrow to add it to the selected elements list. And then there's also mass of microorganisms in the clarifier. So it's the two main tanks where the bugs are living, effectively, is what we're telling it here, is the total mass of microorganisms are in the tanks. And there's going to be some negligible amount of microbial mass in the pipes, but for this we can just assume that the volume of the clarifier and the bioreactor is so much larger than the volume of the pipes that we don't necessarily need to include those other elements as where the total mass is. Now the next thing it needs to know is where are we wasting sludge? And so there could be multiple sludge outflow nodes in a really complicated network, but for us, This solids retention time, just designate that it is sludge 4, where the sludge leaves the system. And now with those things defined, we can calculate the hydraulic residence time next time we do a simulation. It'll go from being blank down here to actually reporting a value. So click OK, and then let's simulate again. So simulate, steady state balance. Run it, solution found. And then down here at the bottom, now it says it's 4.46 days. Notice that the volatile suspended solids in the bioreactor is about 2,000 milligrams per liter. And that's right in a typical range for what you would want the microorganism concentration to be in a bioreactor. We use volatile suspended solids as kind of a surrogate for how much microbial mass is inside the bioreactor, because there's a little bit of volatile suspended solids that's the actual waste. You know, like there's BOD particles that are suspended that can be broken down, but by far the majority of the mass of volatile suspended solids in the bioreactor is the microorganisms that we ourselves are growing in order to break down the BOD. So we know a lot of things now. We know, for example, the characteristics of the effluent. We know what the sludge strength looks like. You know, we've got a really high BOD sludge that's going to have to be stabilized some way, whether it's land application or after it's dewatered, maybe it could be incinerated or it could be worked into bricks, or there's lots of different things we've talked about for ways to deal with sludge. But now we know some of the characteristics of the sludge. So the first thing that we wanted to do here is find the effluent of the BOD, nitrogen, phosphorus, total suspended solids, and volatile suspended solids for this design. And so check mark, we've done that. The next thing that we want to do is if the BOD could be as high as 15, you know, 6 is pretty low. What if we were allowed to discharge 15 milligrams per liter? Could we get away with a smaller aerator? So this is really where the beauty of a simulation system like this becomes obvious, is if you were going to do the hand calculations for trying out the new size of a, you know, like reduce the size of a bioreactor and find out what's the effluent characteristics, you're like 2 pages of hand calculations, lots of crunching the numbers in the calculator. But we can just do it as simple here as double click on the bioreactor, reduce the volume from 4,000 to 2,000. What if we cut the volume of the reactor in half? So choose 2,000, then we simulate steady state balance, have it run, solution found. Okay, now our BOD went from 6 up to 11. So we've cut our reactor size in half, and we're still an acceptable discharge of BOD. The nutrient removal also gets a little bit worse as the reactor is smaller. But let's try going even smaller. What if we made the reactor 1,000 cubic meters? Okay, simulate steady state balance, run it. Okay. We went too far. Now the BOD is 30 milligrams per liter. So like this is the classic engineering technique of iteration, optimization, kind of trying to find that ideal volume, which I think when I did it before was 1616 cubic meters. We run the model there. We get 15.01 milligrams per liter of our effluent BOD. So, I mean, it's hard to overstate how valuable it is to have a system where you can change a parameter and instantly see what's the effect. In the background, it's running so many calculations having to do with aeration, because when I change the reactor volume, then the flow rate of air required also automatically updated. In the background, it's doing calculations related to the solids retention time. We are having some updated concentration of the volatile suspended solids. All of those things are impacted by having a smaller bioreactor where we've kept the recirculation amounts the same. So if the BOD can be 15 milligrams per liter, we could go for a reactor that's as small as 1616 cubic meters. But let's say go back to 4,000 cubic meters, and this one I'm going to let you to try and adjust without me narrating along. Let's go back to 4,000 cubic meters. One of the big expenses here is going to be pumping. And one of the pumps that we're going to have to put in place is pumping the sludge from the bottom of the clarifier. We're sending a lot of sludge into the bioreactor. Could we get away with less? So let me run the simulation again, go back to our kind of first solution where we were using the 4,000 cubic meter. So this is our original solution. So what I'd like you to try and determine is how much could you affect this clarifier? If you reduce the flow rate off the bottom of the clarifier from 15,000, how low can you go and still get 15 milligrams per liter of CBOD? So try to find what's the minimum underflow, and we're still going to waste 500. So when you change the, like from 15,000, if you go with 14,000, it'll still send 5,000. We still want 500 to be going to sludge, and so it'll just reduce the amount that's going into the bioreactor. So let me pause for a second and give you a chance to try and find that minimum flow rate. Let's see. You may have to redefine the splitter to make sure that it knows that 500 should still be going out. Once you change the underflow from the clarifier, you may have to go back in for the splitter and swap out the side versus the main. So you see, I previously had said that the side was 14,000. Well, we don't have 14,000 anymore if I take my underflow to 7,000. So what I did instead is I said I want 500 to go out the main. And so if I've got 7,000 coming down into the splitter, it sends 500 out to the main, which is the sludge discharge. And then the balance, it will recirculate. So if I have turned down the underflow from, what was it before, 15,000 to 7,000, I don't take much of a hit. So we can change that even more. Maybe if I can get away with an underflow of 4,000 cubic meters per day and run that simulation. How does that affect the BOD? Took it up to 15.06. So it seems like that's a pretty good sludge recirculation. And so we went from, I don't remember what the original sludge recirculation was, 15,000. We've cut by like a third the flow rate that needs to come out of the bottom of the clarifier. So that's going to allow things to, number one, settle a lot better than they were before, but number two, the pump doesn't need to be as large. All right, it's 12:50. We're out of time. Save your file. You won't be able to use this software unless you're on campus, because the server's running on campus. You can't run this at home unless you connect to the VPN. Possibly you might be able to run the software from home if you have the VPN running. We're going to continue working with this software on Friday. We'll look at modeling some trickling filters. So I'll see you in class on Friday.